Carl's been spending years and years down and pestering the people at the University of Florida, and a lot of the students there have benefited from his take on things and his approach to modeling, and Ed is one of those. So Ed took those ideas, applied them to his master's, took off, decided to work in New York, and although everything in New York was great, he decided the fishing wasn't good enough. So he came back to Florida, where he grumbles about everything except for the fishing. Did his PhD with, he did his master's with Bill Pine at UF. He then did his PhD with Kai Lorenzen at the University of Florida, and now he's doing a postdoc with Kai as well. And he is up here for more or less the week, working with me on some crazy theoretical stuff that has no relevance to what he's going to be talking about today. Today he's talking about integrative evaluations of stocking red drum in Florida, and I will leave it to you.
Thanks for coming. This is quite an impressive seminar room compared to what I'm used to at very impressive seminar room. Thank you for coming. So when I was doing my master's, I was looking at relationships between these little small fish that lived in types of aquatic vegetation in this coastal river in Florida. And I needed a volunteer to come out and help me, so I had my girlfriend at the time and my wife come out, and she was in a boat recording data. And I was wearing a snorkel, basically under the water, flipping away at plants and stuff. And I hear this boat pull up to us, which often happens. They want to know what you're up to, why you're sitting in a river. And so I pop up and the guys ask, what are y'all up to and everything. And I'm struggling to get my mask off and explain to them, well, we're looking at the relationships between these small invertebrates and small-bodied fish and the different types of macrophytes here. And my now wife just says, no science. And he just smiles and boats off. And everything was fine. And the point of this is that I guess science means different things to different people. And I don't really know what it meant to him. But where I'm at right now is I'm understanding my role as to predict outcomes of alternative management strategies, a really utilitarian-based approach to science. And I think with this, understanding the trade-offs inherent to a lot of natural resources is very critical. I say that they're inherent because I understand that I believe that most natural resources are typified by at least these two common goals, one of which is to sustain a natural resource for some intrinsic aesthetic or a long-term socioeconomic objective, sometimes, or for this talk, I've termed that conservation with a little c, and then to gain some social satisfaction, economic benefit, or market value from using that resource now. And over the long term, these are obviously quite complementary, but in the short term, they can conflict, where using a resource now means we can't conserve it for later. And when these conflicts happen, you basically have a trade-off, where more of one objective may mean less of another. And if management's primary goal is selecting the strategies to best make use of these trade-offs or maximize these trade-offs, then my job is to understand or predict what trade-offs would come from the strategies. Forgive me, it's possible that I've been infected by small members of the Van Porten family. Try to make it through the presentation fine. Narrowing down quite a bit to recreational fisheries, I think that trade-off's seen a lot between the socioeconomic value that's associated with high fishing efforts, so lots of fishing trips, and high catch or harvest, basically things that kill fish. And the conservation values associated with preserving wild fish abundance and genetic structure at some level. And so traditional management strategies aimed really at restricting the amount of harvest, things like restricting size limits or bag limits. At times, they can have the unfortunate outcome of decreasing the amount of socioeconomic value if they're actually decreasing the effort. And so, increasingly, some places have been interested in stock enhancement for recreational fisheries, where this is defined as the addition of hatchery-reared fish to wild populations, with kind of this implicit goal of trying to circumvent this trade-off, saying if we can just stock more, then we don't have to reduce the effort, and we can hopefully have these sustainable wild fish populations too. And so a valid question is, why is this being considered in Florida, where I'm working? And so background of Florida, it's got a tremendous amount of coastline filled with all these little bays and estuaries and rivers, and these provide really abundant, aesthetically pleasing areas in which to go fishing for a whole variety of different species, all in shallow water, all in small boats, and that are available, many of them, for 365 days a year, so you can always go out and fish. And so what this has led to is that there's enough effort to actually merit some concern of overfishing simply from the recreational fishery alone. One of the species that's a concern for is the red drum or redfish. When I'm in Florida, I say redfish. When I'm other places, I try to say red drum. It's a cyanid, Cyanops oscillatus. It's this fast-growing, long-lived species. It gets to about 40 years and probably about 25 kilos or so. And it has this shift where the inshore fisheries, the ones that inshore fish that we target, they live around oyster bars and mangroves and such, and then they grow big and move offshore, and no one really fishes for them. So it's exclusively a recreational fishery. It's this really popular target species. They taste great, they fight well, all of these things we like. They hit topwater lures and such. There's been increasing effort over the last few decades and the concern about increasing effort, but actually the management regulations have been relaxed. So they've doubled the bag limit of half the state, and unofficially that may be in response to pressures from other species that are being targeted, that are being federally managed, and they have to crack down on, so they're trying to give the fishers something that they can target. In addition to this, the redfish is considered for enhancement because we can rear them in a hatchery. They're not particularly cannibalistic, and so there's this interest from the state, both the governance and the stakeholders, in trying to be able to stop red drum. So my research objectives were to assess basically the potential enhancement. They've done it a few times in the past, and they're gearing up to probably use some of the money from the BP oil spill to try to build hatcheries and stock these fish again. And so the first objective was to understand what elements of this enhanced recreational fishery system were really important. All elements can be important in the system, but when I'm going to model it, I needed to try to figure out which were the most important to represent. The second was an attempt at empirically evaluating some of those relationships, the angler-effort relationships, which didn't yield a particularly clear answer, but that's important too. The third was to basically quantitatively predict the outcomes, and this was a simulation approach. And then that was extended to this fourth one, which was to look explicitly at the trade-off shapes realized with enhancement relative to some other strategies. And if there's time, I wanted to mention some of the things that I think about how this enhancement could affect the actual resilience of the system as opposed to just the expected outcomes.
Sorry.
So this first objective was basically just accomplished through a review and the synthesis of the literature, trying to understand what information should be taken into account before a place begins a marine and recreational stock enhancement policy, and this had the benefit of informing me of what needed to be put into a quantitative model. So I based this loosely off of some of the work that my advisor, Kyler Ensign, did, which was designed at relating these situational variables, things about the system itself, ultimately to the outcome through two paths. One heavily relying on the stakeholders and how they felt or acted on the system, and the other through direct biological influences. And basically, I adapted this to try to understand how stock enhancement would get the stated goals of it, of increased satisfaction, increased economic impact, which is the market value, not the benefits, but it's actually basically the number of trips, the amount of money spent on it, and hopefully do so while sustaining the wild populations. So the fisheries path requires stock enhancement to increase the abundance of fish and either lead to increased effort or catch rate, or both, even though they work against each other. And then hopefully lead to the impact and maybe the satisfaction, hopefully without that. The stakeholder path is interesting because it circumvents all this and basically says stock enhancement could potentially make people happier just if they like it, right? So the key linkages were the ones between these. So for enhancement to increase fish, we had to pay a lot of attention to the recruitment dynamics. For the increase in fish to lead to changes in catch rate or effort, we needed to know the angler effort dynamics or pay attention to that. And then for this to scale up to the actual satisfaction, we had to look at how the catch rate or the CPUE was related to the satisfaction of the anglers. That's the utility, which most people recognize as part catch rate and part non-catch rate. And then this all comes to basically how much satisfaction or investment is there from the stakeholders that's motivated by stocking. So the key linkages here were these ones. The one that I focused on for the second objective was this angler effort dynamic. And that was trying to understand, is there empirical basis to decide how much effort will change when the abundance of fish changes? And this matters quite a bit for stock enhancement because you're considering increasing the number of fish there. And so to look at this, well, this is why it matters basically. It determines what the recreational fishery is. Is it some coupled predator-prey system where as the fish abundance changes, the angler effort changes relationally to that? Or is it more some decoupled extraction where the angling effort, the aggregate effort, just increases or decreases as functions of, say, the population or over time? And if it's the latter, you might expect some of this built-in resilience to affect it, and if it's the former, you would expect that. If it's the latter, there would be less so, right? So this is actually a fairly important question, and surprisingly one that has received relatively little empirical evaluation, at least in the recreational fisheries. And part of that is because it was quite messy. So we looked at a few different fish species from the inshore fishery and saw if we could predict the effort as a function of the estimated abundance from those species using a suite of relatively standard regression type of metrics. The overall answer of this was that while the effort by fish abundance model was the most parsimonious and it could explain a fairly high amount of the data, particularly if we added in some of these extra environmental or economic metrics, you could make almost as good of a model with a null model, basically predicting effort as a function of just calendar year. So it wasn't very clear if there were these causal relationships, and this was a picture of the difference model here, which is, it's basically a mess. So what we drew from this is we couldn't really guarantee that there was this strong angler effort relationship, and this is partially because the data, these one-way trip data, we started assessing stocks in Florida around the 1980s when stuff started to be overfished. Regulations were enacted, so the fish populations have been gradually increasing at the same time that the human populations have been gradually increasing. And so when you put this together, there wasn't a whole lot of information to pull out of it. So we're not really sure if they're coupled or not. And while one implication of that is that there could be some real need for some natural or manipulative experiments to try to get at that, the other one is that, at least for the stock enhancement modeling, it was important to represent probably a range of different angler effort dynamics, and I'll get to that in a minute. So this was trying to put the simulation model together to predict some both absolute numbers that would be useful to the state of Florida, how many fish would you need to stock in order to get this response, and then some more general trends saying if we pretend that theoretically it's possible that we can stock a whole ton of fish, what are the types of results we could see? And that's an important distinction because a lot of times the amount of stocking that actually goes out in these marine systems may be so small that we don't actually see the main result, or it's swamped out by recruitment variation. And so, because we're not in Florida, I'm going to focus here mostly on the general trends of these expected outcomes of stocking. So we wanted to look at a lot of different response metrics to try to capture not only the ecological things like the proportion of wild spawning biomass that's extant after you start stocking, but also some of the socioeconomic things. So we looked at effort as a proxy for the economic impact because it's the number of trips, the satisfaction associated with catch rate, and I'll explain that more in a little bit, and the socioeconomic value is basically scaling that satisfaction per trip up by the number of trips. The total catchable fish is just a partway thing. That's more to explain it. We wanted the model to be flexible with respect to the sizes and the numbers of fish stocked, and that's particularly in order to represent the recruitment dynamics, because a lot of times people stock fish before they've exited that density-dependent mortality phase to life history. So that had to be represented. And the first results were these more average, what I would term average outcomes, so that's a bit of a misnomer, but really what would we expect with moderate values of the uncertain parameters, and then look at some possible outcomes given some of these uncertainties, specifically with the responsiveness of the effort, that's angler effort dynamics, and how much the satisfaction was driven by catch rate versus driven by other things like just inherent satisfaction from going fishing, things So to do this, built an age-structured population model following pretty standard forms. It had a couple things built into it. One is termed as unpacked recruitment, and that's basically accounting for both the size and the density density-dependent effects on mortality of the little fish. The other is that it tracks these wild fish, hatchery fish, which are the wild-born progeny of the hatchery fish, and then the stockfish, which are stocked each year. So it tracks these populations to keep a loose tab of really the genotype in a very coarse way. It has dynamic angler effort, following some of the stuff that's been published, using these logistic models to vary how strongly effort responds, fishing effort, to a change in the abundance. And we modified some satisfaction and value functions from the work by Cox and Walters and Cox et al. So this was just a simulation model, completely theoretical, but in order to actually produce the numbers that the state wanted and to make sure that things made sense, I tuned it to the available data, and I say tuned as opposed to fit, because what I did was I ran the model to equilibrium and then estimated some of the scaling parameters, the recruitment at unfished conditions, the catchabilities, and voluntary discard rates, such that at equilibrium conditions it was producing, the simulation model was producing similar catch rates, effort, and harvest for a specific area of Florida that we could return from the National Marine Fisheries Service MRIP data. MRIP is Marine Recreational Information Program, so it's basically their survey data. And the data is not really, we don't have a long enough time series of this to do a full time dynamic fit, but it was enough to get us in the ballpark and make us think that the numbers we're using here at least scale it to an area that's reasonable. But the purpose of this was not parameter estimation, it was simulation. So to represent these different metrics, it was a little bit of a challenge. So some of you are probably much more familiar with these contour figures than I am, but I will walk through one to explain it because they pop up a bunch. Basically, for a single response metric, say the vulnerable or the total catchable fish, we theorized that we could stock a whole different range of numbers of fish stock, from lots of fish stock to no fish stock, and across different sizes from really small to really large. So if you imagine basically a grid going up and down and across this, at each intersection, we simulate stocking that number of fish at that size. And then we return the outcome here, the total number of catchable fish that would result, and we color code that. So the darker colors are higher numbers. So this would say that if you stock a lot of really large fish, you get more catchable fish out, which it should say that. So these were the results from the what I termed earlier, that average approach, or using a moderate relationship to catch rate and a moderate relationship to the angler effort. And a couple of the things to point out, one is that you can increase some of these socioeconomic metrics, the satisfaction per trip, or the total number of trips, if you're willing to stock a lot of particularly large fish. And what's notable is that stocking lots of small fish gives virtually no benefit at all from socioeconomic. However, stocking a lot of small fish still does decrease the total amount of remaining wild spawning biomass. So basically, stocking small fish has a real negative effect without giving the potential for this positive effect. The other thing we wanted to explore with this was how different the response rates were to the abundance of fish here. So what we assumed in the last one was this linear response here. This is with fishing effort to the vulnerable fish. Could also theorize a completely flat response, which is effectively saying even though we stocked more fish, no one made additional fishing trips. Fishing effort remained the same. Or a really flashy response where a little bit more jumps a bunch of latent effort into the system and a little bit less empties it out. And so these results with the different effort dynamics in the columns here, this is the flat, this is the moderate that we just saw, the linear, and this is the really sharp. And the response metrics here in the rows, the satisfaction, the effort, and the wild spawning biomass. And the key point is that with a really flashy response, you can get the greatest increases in your effort, your economic impact, but it's not nearly as good as the flat response in terms of the satisfaction and utility, and that's the interplay between the effort and the catch rate, right, in that ratio. And so a little mini trade-off in there between trying to maximize the system for economic impact versus economic benefits. Interestingly, for the wild fish, there was very little change, and there is actually a change here. It's not as easy to pull out in those figures, but it does affect it. So you have lower numbers of wild fish at lower stocking abundances with a really sharp flashy response.
I'll put it up at the time.
Should work. So the other thing that we wanted to explore here was the catch rate oriented satisfaction. Everything we've looked at so far assumed that the satisfaction or catch was high or full, and we basically stepped that back to consider if less satisfaction or if catch rate was less important than some of the other attributes. And so here we have the same effort responsiveness in the columns and the different catch rate orientation in the rows here. What we've seen already has been the full, and then the half, and basically no satisfaction from catch rate at all. And the main point of this is that basically the socioeconomic benefits can be achieved as long as there is some effort responsiveness or there's some satisfaction that's driven by catch. And those are assumptions that we believe as managers we are comfortable making. The result of this being that basically, yes, we can achieve some of the socioeconomic objectives with stocking, particularly if the larger fish are stocked and there's a little bit of effort or satisfaction requirements, caveat being that those are going to work against each other. So the more responsive an effort it is, the greater impact, but the lower satisfaction given the catch rates. Stocking is unlikely to meet the conservation objectives, and this really wasn't sensitive to too many of the parameters that we looked at here. The major caveat, though, is that we've assumed the conservation is wholly supported by the wild fish as opposed to the stockfish. If the stockfish are as good or as desirable by society, then this is not really an issue. So the overall message is that stock enhancement, which this is not surprising, is likely to cause a loss of wild fish, and you get this trade-off between some of your socioeconomic outcomes and maybe the conservation-oriented outcomes. And that was what I wanted to investigate for this fourth thing here, looking at specifically what the shape of these trade-offs were. And what I mean by that is specifically how much of one objective needs to be given up to achieve one unit of another objective, right? And so if this is linear, it's 1 unit of objective 2 must be given up to achieve the next unit of objective 1. If it's this, what I'm terming a concave down, then you have to give up less than 1 unit to get the next. But if you have this convex up here, then you have to give up a lot of objective 2 to get that additional unit of objective 1. And so by looking at the overall frontier shape that is realized under different management strategies, we get some intuition in general terms about how effective or efficient that strategy might be, particularly if it can be compared to other alternative strategies out there. So to do this, it looked at basically the relative values of the value representing the socioeconomic objective and of the wild spawning biomass representing the conservation objective. We plot the different outcomes of each scenario in terms of the scenarios, meaning the numbers of fish stocked and how many fish stocked, and connect those outcomes based off, I think, the size of fish stock, how big they were. And this gives us the shape of the trade-off. And so this is the one for assuming moderately responsive or linear responsive angler effort and a relatively high satisfaction from catch rate. And so these points here, these are the different actual outcomes simulating the stocking of these. And so, and they're connected just simply by the trade-off lines here. So as you move from right to left, we're increasing the number of fish stocked. And as these lines space out, the size of the fish stocked. So one way to interpret this is saying if you're stocking only small fish, you're giving up a lot of this conservation objective without achieving your socioeconomic value. Right? And if you're willing to stock these much larger fish, you can get this increase in socioeconomic objective, but only after you've lost a lot of the wild fish. Right? So it appears to be this unfortunate concave up shape. With the one interesting caveat is that once your system is already down here, it's a low marginal cost to increase the socioeconomic objective, right? Which is interesting, and that actually implicitly says a lot of how we value those last few units of conservation objective. Whether that's a linear function is just summarized here. We explored this with, again, some uncertainty, and this was uncertainty in actually how the conservation objective was represented by wild spawning biomass, by the amount of wild fish remaining. What we looked at before was this linear relationship here and yielding that trade-off, and we supposed there might be some asymptotic relationship, which is effectively saying that at really low amounts of wild spawning biomass, there's still substantial conservation objective realized. And contrasted that with a logistic relationship saying that basically as the spawning biomass falls from say 0.4, that's 40% of the wild fish compared to an unfished levels remain. As that falls down to about 0.2, you have this steep decline in the conservation objective, and then the last few units, basically less than 0.1, not so much. The main point in this is it did little to actually change the shape. It shifted the shape around or made it more extreme, the actual trade-offs, but the shape itself didn't change at all. The other uncertainty was this relationship between it's the satisfaction, but really, given how it's calculated here, the satisfaction per trip scaled up by the number of trips. The key thing to investigate is how the satisfaction is related to the catch per unit effort. That's a key link in the model. So what we assumed before is a linear relationship here, and we can similarly suppose this asymptotic relationship, which is essentially diminishing marginal returns. As you catch more and more fish, each additional fish per unit effort is worth less than the previous one, or an exponential function where at high catch rates, the satisfaction is more than proportional. Right? And so again, this didn't absolutely alter the trade-off shape much at all. You do see that with this asymptotic relationship, you just get a lot less of the socioeconomic objective relative to if you assume linear or exponential. But none of these things are dramatically changing the shape of the trade-offs here. And so this is an interesting question because stock enhancement happens quite a lot. So if the representations that I've made here are suggesting that this is not a particularly efficient strategy, then either I've done a really bad job of representing them or I've left something out of the model, or there's some other component of this satisfaction that is well, it's also left out of the model, is not included here. So what we theorized is that a potential relationship between basically satisfaction from stocking and the amount of stocking, and this was theorized to look at specifically what would it take to change the shape of this trade-off. And what it would take is basically a group of people, whether those are actual managers or politicians in the governance system or stakeholders themselves, are attaining some great utility from stocking as long as it exists. And that would have to be quite sharply asymptotic such that that satisfaction is zero when there's no stocking at all, and then jumps up very high as soon as you see the hatchery truck go out, as soon as you hear that the hatchery is being built, but isn't affected actually at all by how many fish are put out. It just has to go on. This is theoretical, but I think it is possibly not so far-fetched given the legacy of stocking in different places throughout the states here and apparently Canada as well. So what this did is what we designed to do, which is it can actually alter the trade-off shape, but it's interesting where it's altered and how. And so by stocking really small numbers of small sizes of fish, you actually can get a closer to linear increase, meaning that you give up some conservation and you get about that much socioeconomic objective at the fewest numbers of fish stock. And if we had done more iterations than this, it would have curved over even more. What this is representing is basically stocking to fail or stocking only to achieve that social satisfaction from people wanting to see the hatchery trucks out there. It's stocking as few fish as possible, as small. The final thing that we wanted to look at with this was look at this trade-offs that might be revealed forcefully by examining alternative strategies that one would consider. And so keeping with the idea of not pursuing these restrictive strategies, changing the bag limit or the size limits of fish, we looked at more augmentative strategies, things like either habitat restoration, or improving the facilities, so better restrooms or ramps at the boat, or trying to foment this idea of catch and release fishing so that more fish are being returned to the water. So this is a really, really coarse look at it, meaning that they're represented at a very coarse or crude level in the model, these strategies. But what it reveals is that something like stocking, which has this sort of inherent negative effect on the wild fish, is particularly less advantageous than some of the alternative strategies, such as increased catch and release fishing. This includes the discard mortality and all of that. Or the direct habitat restoration or direct satisfaction improvement. These other options that are out there, and it should be pointed out that all of these things, with the possible exception of catch and release, are probably expensive to implement, right? Building hatcheries costs money, so does habitat restoration, so does facilities improvement. But it would suggest that if this is representing, or to whatever extent this represents reality, stocking is really an inferior approach towards achieving these objectives. So the overall message from this is that assessing the trade-offs, to me, I thought this was quite valuable because it was a clear way of comparing the strategies to alternative ones. It suggested that the stocking is this inefficient trade-off, and that it's probably less than these alternative management strategies, although it didn't account for exactly how much the cost would vary between implementing the different ones. And that would be the case unless stockholders are really, really in love with, stakeholders are really, really in love with stocking. And one of the points from this is that the stakeholder opinions, how much they actually care about the management strategy implemented, may matter quite a bit in terms of the overall outcomes. And that was something that I wanted to explore a little bit, and this has been largely theoretical. To me, it's some of the most interesting stuff, and it's trying to understand how stocking might have an effect on the resiliency of the system, that is, the ability of the system to withstand and actually rebound from this likely but unpredictable change. So all of the metrics that we've looked at so far are all about increasing things, so increasing catch or increasing value, or even or decreasing by the smallest amount the numbers of wild fish. And that is one way of looking at things, and another way would be to say that our goal should be more resilient systems that may not be optimized, but they may do a good job of withstanding disease, environmental change, economic downturns, etc. The reason being that these optimized systems, when they're tuned for these really specific circumstances, are possibly more likely to fail when those circumstances change, and this unpredictable change is really inevitable in the natural systems. So I think it's possible that given the amount that stocking has been entrenched in some of the management strategies, and how it can potentially affect the stakeholder satisfaction in and of itself without having to filter through those increased catch rates, that stocking may potentially tip systems' resiliencies towards less resilient or more resilient. And I've come up with two really hypothetical scenarios, and this is just me thinking. I haven't empirically proven this, but this is going through the literature and seeing how I think these could happen. And I'd be really curious to hear feedback from people here of whether they think these are realistic or not. And the first is stocking towards greater resiliency, the investment approach, where stocking might focus the stakeholders on the actual resource. People see stocking, they care, they go and visit the hatchery, they care about the fish, and that leads them to value the resource in some way. And that value of the resource may actually lead to investment in the resource management itself, and that investment is critical for this self-organized co-management participation in the actual management that a number of papers have noted as being really key for increased resilience. And this participation then gives the systems the ability to be flexible, and this flexibility lends the resiliency to the system, or resilience to the system. So that would be one theoretical way. The other direction is termed the panacea approach, following a paper that Brett and Robert Arlinghouse wrote. And this is where stocking may be perceived as a quick fix for this inherent trade-off. Instead of actually worrying about this, we can stock our way out of the problem. We don't need to conserve this species. Here, you might actually have a decrease in stakeholder value of the wild system and its managements, and this would be concomitant with this potential decrease in actually the wild fish, leading to a system where stocking becomes entrenched, where you need stocking in order to prop the fishery up. And the result is stocking is this panacea. It can't change. You have to use it, and there's little flexibility to adapt if you have substantial changes in the system, and that's the lower resilience. So it's interesting for me to think about what determines which way a system tips. And I think that boils down to basically how people perceive stocking. Is it this investment in a precious and useful resource, or is it more a technological fix panacea approach? And there's been some work studying exactly what determines how people think and how people's opinions change. And there's a number of indicators of this. And one of the interesting things, or one of the things I'm most interested in doing now, is trying to actually quantitatively predict how change in opinions might happen, the same way as we try to predict how changes in populations of fish or other animals would occur. I think this has probably ethical considerations with it, because the actual change of people's opinions could theoretically be a valid management strategy that could be engaged in. And then there's the fine line between really predicting what outcomes are possible and advocating for what we should do by trying to change people's opinions there. And basically to try to stay away from that and to try to stay out of the advocacy, I'm most interested now in looking at, are there ways that I can empirically model the shifts in public opinion and actually in public judgment in relation to different management strategies. So I want to thank the people that have helped me out a lot with this. Tyler Enton was my primary advisor. Sherry Larkin is an economist at the University of Florida. She's the co-advisor. Rob Ahrens, who is familiar to several of you, was tremendously helpful in all elements of this work here. And Mike Allen and Chuck Adams were also on the committee and were really helpful too. And I have benefited a tremendous amount from talking to Carl, although sometimes I have been called an idiot for talking. But Carl's helped me a lot in this, although I do not hold him responsible for anything I put up here. I also wanted to thank, funded through University of Florida's School of Forest Resources and Conservation and the National Science Foundation Migrate Program. They funded all this work that was part of the dissertation. So thank you.
A big feature of your talk is these trade-off plots. Is there any chance you can go back to one of them so I can just, because...
Do I want to?
I'm a little, I'm not totally quick. I couldn't, that's great. Any of these is great. That's good.
Okay.
So I'm a bit slow. I didn't quite keep up with you about these axes. But of course, the shape of these things is going to be determined on how you scale these axes. But right now, you're just assuming they're linear. And how are they scaled? Like this conservation objective, I mean, does this really represent the value from a conservation perspective, or is this some linear metric of biomass? Like, what's going on here?
So what the assumption that is implicitly made, and it's a pretty substantial assumption, is that depending on, it's that the conservation objective is a function specifically of the wild spawning biomass, the proportion of wild spawning biomass remaining, right? And so what I just showed assumes this linear relationship.
But if you were to put, if you were to superimpose productivity over that, it would be productive at like 0.4, right? Or something similar, like at some intermediate stock size, and you wouldn't worry about conservation above a certain level. I'm just saying that it would change that plot if you, if you took into account like the probability that the stock was going to get into trouble or something similar.
Right, so what this is basically I ran the model to equilibrium so that the initial spawning stock biomass in absence of any stocking is around 0.4, which is actually, that's the far right side.
They're starting out.
They're starting out
at a good level.
At a reasonable level. They're not starting out at an unfished level.
Okay.
And then I look at the relative values of that. So these are all on the relative scale, scaled from the highest conservation objective in absence of stocking, basically, all the way down. And the question is really valid because it's a pretty powerful assumption to decide what determines conservation objectives. And so that's why we looked at some of these different.
So the related question I had was you seem preoccupied with the shape of the trade-off space. Lots of people produce perverse and odd-looking trade-off space and just say, well, we're going to pick this. I mean, I'm trying to understand why you're so worried about the shape in the trade-offs as opposed to the cost of finding a desirable point on it. Like, you want reasonable conservation and reasonable social-economic objective. You can pick a point. It doesn't matter what the shape of the trade-off
Right.
space around it looks like. Why are you so worried about shape?
Because I'm interested in whether this is a reasonable strategy compared to other strategies. But you're absolutely correct. Given a certain strategy, you could just select any point, given this is how much we're willing to pay, and this is as good as we can get. And the shape is really secondary if you're fixed within that strategy, I think.
Yeah.
No, it's worse than that. When you have a concave structure there, the optimum tends to be at one of the other extremes. I don't know how you weight those two objectives. It's not there's not a good balance when there's a strongly convex or concave structure like that.
There is a nice
Balance is that.
There is a nice balance. It's right there. I can see it. There's a point where you could have moderate conservation and moderate socioeconomic objective. I don't care whether or not you decide to walk into these other
We're
parts.
giving up a huge amount of socioeconomic objectives.
Relative to what? These extreme things you don't want to do anyway? I'm saying if you put another management strategy over there, all the points might lie, regardless of the shape. Let's say they're nice, like Carl's saying, they're nice concave shapes, or convex, I don't know how you describe it. But they were all underneath the points on there. I would pick this strategy.
Right, absolutely. So that's why I looked at the alternative ones to judge that, and this should have more work done to it to evaluate the actual cost.
I think you need to know the shape, because if you are under the curve, there's a possibility of improving both the conservation objective and socioeconomic objective by moving toward that frontier. Basically, what is plotting is a parallel frontiers for different how you weigh and how you measure these objectives. So knowing the point just doesn't tell you if there's opportunity for improvement on both sides. So you need to know the shape.
I guess I think it's not the shape that's so important as the slope. Because if the slope is minus 0.5, it means there's a 50-50 trade-off. Whereas if the slope is flat, if the slope is lower, it means you're trading off a bigger conservation objective for a smaller social and economic value. I don't know if that makes sense.
I'm not able to think quickly enough to respond intelligently to that right now. Sorry.
I'm just curious, do you have any plans to actually interview people and collect data to see if your relationships actually hold, or might be something completely different?
Do you mean with respect to?
With respect to how effort changed with research satisfaction, how when you had like in your end you have two different theories of
All
how
of the
this
assumptions that
works?
have been made? Yeah. So there's some literature that I can lean on that's been published, and that would suggest that catch rate is a really strong component of the overall satisfaction. But strong doesn't mean that it dominates the overall satisfaction, right? So it's typically the element of the satisfaction that anglers have the least control over, so it may be the most important to them. Say 75% of the satisfaction is just from getting out there and fishing, but they get to control that to some extent. They get to decide where they go and how much they fish, more or less. But that catching, that's the one that's in flux there. They don't have complete control over that. So there is evidence to include these in there. The question is how are they parameterized for any specific model? And in absence of that information, I've tried to basically bookend it and look at a range of different relationships from really strong to non-existent at all. In addition to that, other people in the lab that I'm still part of, Kyle Lorenzen's work there, are specifically looking at both these state preference surveys and also the discrete surveys, try to understand theoretically how people's relative satisfaction or utility would change from a hypothetical management strategy. There's issues with that because it's hypothetical and you're relying on people to say what they would do as opposed to the revealed preference choice of actually doing something and seeing what they have done. And there's been some work that's done on that, and that's typically in the natural resources economics work using travel cost methodology and random utility modeling. The short answer is what I've done here is, I believe, appropriate with the literature, but is also trying to respect the fact that there's a lot that they don't know about this exact system.
Sorry, just a follow-up. I was curious too about your assumptions about like how people perceive having a hatch rate,
Right.
and like they might increase satisfaction just by knowing the hatch rate there, but they might not be doing anything.
That's completely theoretical.
Yeah.
That's something that we actually are trying to do because Florida, with this BP money, is going to try to build a hatchery. So we're actually trying to do surveys beforehand and afterhand to try to see, afterhand is not a word, afterwards to try to see if the satisfaction has been increased by the building of the hatchery even before they start to stock fish. That would be really interesting for us. This is completely, what I've proposed here is completely theoretical, and it's based off the observation that stocking happens. And so unless I've completely messed this up and stocking is actually a good thing for the socioeconomic stuff and wild fish, then there has to be some utility. From economic utility theory, the fact that it happens, someone or something is benefiting. And that curve could represent stakeholders, but it could represent politicians or governance agents or managers just as well, who may have an increase in their satisfaction or their utility of stocking regardless of what it produces or how it affects them.
Amanda.
Yeah, you might want to bring in two of the international global conservation approaches on this. One is that the IUCN doesn't actually allow you to use any form of culturing, enhancement, stock, any of the stocking as part of your evaluation of the conservation status of wild populations. So it's worth just bringing that in because explicitly any stocking is above and beyond any conservation status. And likewise, stocking is considered a form of supplementation. It's not reintroduction, supplementation. And there are method guidelines on whether that is conservation appropriate or conservation damaging. For the most part, from a perspective of wild populations, it's often conservation damaging, and not always, of course. So the reintroduction specialist group guidelines would be another big important tool to bring in here. So when you talk abstractly about whether stocking is a contribution to wild populations or not, and whether it meets conservation objectives or not, there is actually a well thought out literature about that that might be worth bringing in. And then just following up from that, I was slightly, having really enjoyed your talk, a little perplexed by it, but it's because I'm slow, but having really enjoyed your talk, you got to the end and said, well, I don't want to go to advocacy, so let me retreat back into the world of science. And I was slightly stunned by that, because surely if you put this degree of thought, and you have a number of other resources you can marshal to try to assess this properly, you have an obligation to get involved in helping to determine management approaches and responsibilities in this context. So why would you retreat from it so very explicitly and proudly?
Well, I'm not sure if it's proudly. I don't have a tremendous amount of experience as a scientist, and I am attempting to move forward cautiously. And I am very comfortable where I am with trying to predict outcomes of potential alternative management strategies, saying what can happen and allowing others to decide what should happen.
And how are you transferring that into the public domain?
Do you mean actually how this information is getting out?
Into accessible public documentation or information that can be used to inform this debate and not just by your colleagues in the scientific community?
Right, so the trade-off stuff hasn't been published yet, due to large part to my messing up some of my economics terms. The simulations for the stocking has been, and since it hasn't been published yet, it's been accepted. And so I've been in contact with some of the local fishing magazines to do little write-ups for it, and that's something that at University of Florida has been encouraged. I've co-authored stuff that goes into the BASS, which is the Professional Bass Fishing Magazine, which may not be huge in Vancouver, but it's a really big deal in Florida. And then we have like college bass fishing and everything. So it actually will go out to regular magazines as a brief summary.
And Brett, one more.
Sure.
Irrespective of IUCN's measures on conservation here, can you explain the conservation objective here in the sense that these fish, when they go offshore, the released ones, aren't they behaving like the wild fish? Why is there this total separation between wild fish and released fish with regards to conservation?
It's an exceptionally conservative distinction to make. I recognize that. And so a couple things in there. I understand it, and basically what I have assumed is that the hatchery fish, or the fish that aren't purely wild, are less valuable than the wild fish, right? But if they behave behave the same if it looks like a wild fish and acts like a wild fish? Is it not a wild fish?
Do they go offshore and spawn?
We don't actually know. We think that some of them do. So this is proposed stock enhancement. There has been some in the past, and I think they've recorded a couple tags from these large adult fish that they believe spawn. But it isn't just the spawning, it's the potential survival of the offspring, the fecundity, and everything else associated with that. What the model does have in it, and I glossed over this, is it allows basically back crossing. So it allows the hatchery fish, which are the progeny of the wild fish, some proportion of them each generation basically revert and are now considered wild fish through the function of natural selection. So it isn't saying that any fish's offspring will always be hatchery. They get to reintegrate to the wild population at some fixed rate, and that's to represent the fact that we expect some of them would do that.
I think we have to, sorry, I think you're still going to be around for a bit, Ed, right?
Yeah.
If you have any more questions, then I think we can move that. I think we have to leave the room. There's a class supposed to come back.